This time, we are given with a homogeneous differential equation where it is claimed that the roots of the equivalent auxiliary equation are imaginary and there are duplication. So we need to show that first before we could apply the general solution intended for repeated imaginary roots for these types of equations. Our equation now is already given with a differential operator. We need to come up with its auxiliary equation in this manner. Hence, we will have the equation m to the power of 4 plus 8m squared plus 16 is equal to 0. Okay? So once we have this, we can actually look for the roots of this given equation and see if they are really imaginary and there are repetitions in order for us to apply the general solution for these types of equations. Of course, here you could always try to look for possible values that you could try, but since if the roots are claimed to be imaginary, the rational root, rational zero theorem may not be applicable here, and there might be some problems as well with regards to different solutions. For factoring. But what I would like to do here is this: what if we let m squared be just equal to k? Okay. What happens then is for our m to the power 4, it's just k squared plus 8k plus 16 is equal to 0. Now, we're just using this, but we'll be returning to that later because it's easier for us to factor this in the form of quadratic equation. And this is actually a perfect square trinomial. Okay, perfect square trinomial here. You could see that the factors here are actually k plus 4 and k plus 4. As we use AC way here, 1 times 16 is 16. Factors of 16 when added will result to the middle term of 8. Of course, you have 16 times 1, you have 8 times 2, but definitely you will be using 4 and 4 because 4 times 4 is positive 16, 4 plus 4 is positive 8, your middle coefficient here. That's why we are using this as our factors. Again, that's k plus 4 times k plus 4 equal to 0. Now, since we have already factored it, what is k? It was actually m squared. So this is actually m squared plus 4 and m squared plus 4 here. These are the factors of our given auxiliary equation. Now, looking into each of the factors, you have m squared plus 4. This is only true if both of them are equal to 0. And we don't need to solve this because they are just the same. This is not the obvious reason of having repetitions because we have same factors. But to the imaginary, let's illustrate that. We have here m squared, you have negative 4 here. Of course, when you take the square root of both sides, m is plus minus square root of negative 4, which is plus minus square root of 4 times negative 1 plus minus 2i, or square root of 1, which is I. These are our roots for m squared plus 4. But there is actually a multiplicity of 2, as this will also give us plus minus 2i here. This is the obvious reason that aside from being imaginary, we have two sets that are duplicated rather. So for this, we have satisfied this claim. Hence, we'll be using this type of solution. Take note that for our roots here in imaginary expresses a plus minus bi. This here, our a is 0 and our b is 2. Okay, take note of that. Because we are going to use this general form, y is equal to c sub 1 e to the power of ax, your a there, times cosine bx. Okay, or we could treat it like this for general form. Okay, for general form, we have e to the power of ax. The first root that is imaginary, okay, imaginary, you will have here times c sub 1 cosine of bx plus c sub 2 sine of bx. Okay, that's for imaginary. But if it imaginary roots are repeated, you will have here plus x. Okay, plus x e to the power of the ax, because this we have the same a because it was repeated. This was what was added as a factor. So you have c sub 3 now because you use c sub 1 and c sub 2 cosine bx plus c sub 4 sine of bx, plus dot 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 until you reach the situation where you have x to the power of n minus 1, the number of times the imaginary roots were repeated. So you will have here times e to the power of ax still times c, let's have c n plus 1 because you don't know what is that, cosine bx plus c n sine of bx. So since we have multiplicity of 2, we'll just end up until here for our roots. So our roots, our solution now, take out of a and b. So you have e to the power of your a is 0x times c sub 1 cosine of 2x plus c sub 2 sine of 2x. And it was repeated. So plus x e to the power of 0x c sub 3 cosine of 2x plus c sub 4 sine of 2x. So we'll end up here because you only have multiplicity of 2. This is 1. This is 1. So you will have the final answer here, which is just c sub 1 cosine of 2x plus c sub 2 sine of 2x plus x times x, because this is just 1, c sub 3 cosine of 2x plus c sub 4 sine of 2x. This is now the complete solution for a given situation where the roots of the auxiliary equation are imaginary and there is actually a multiplicity of 2 for the said imaginary roots. Thank you very much for watching.